Oops, got to finish that part of the lecture. Hopefully we get there in time. And I didn't put the homework. Oh my goodness. Well, I am behind today.
Seven?
Mm-hmm. I am.
We're still looking at the computation.
We're gonna do a little bit today. Yeah, we're gonna finish up. We're gonna hopefully maybe get to 2D. 2D is the same as 1D. It's just twice as much coding.
Yeah.
But we're gonna get through implicit schemes and some other numerical approaches, and then we'll jump back to vorticity dynamics. We may or may not do any Bernoulli stuff, and then we'll head back to computational. So we'll jump back and forth like that for a little while.
We're gonna like learn the concepts, then try to apply it using coding.
Yeah, that's the hope. That's the goal. I found that was helpful in computational. People would be like, we would do these things like create these finite differences. And then if you didn't apply it right away, or like, why did I do that? So. Okay, well, I guess we're having a private class today. All right, well.
15 minutes you get to leave if nobody.
Yeah, right. I mean, I'll make it getting through the first part where we ask people all the parts of the questions very quick. We'll run through that very quickly. All right, I mean, let's start. This is being recorded, so if people aren't here, say la vie. This is where we are. The vorticity dynamics is what'll come next, hopefully. And we'll go back and forth between these two chapters until we get a sense for, I mean, this may end up going a lot longer, but my hope is that it is, my hope is that you like the computational component more than necessarily getting into all of this. We might touch on this very briefly, say in the later half, just talking about specific applications for all of these.
What?
The class has started,
Yes.
So I'm talking. So let's talk about the computational homework. So raise your hand if this is you for the homework. You don't know what that means? You don't know this meme? Yeah, look at his face. It's the pain, but he's like, I'm getting through it. Yeah. Okay, so raise your hand if this is the meme for you for the homework. Okay, raise your hand if this is the meme for the homework.
It's like this.
Okay, raise your hand if this is the meme for the homework. Okay, raise your hand if this is the meme for the homework. Do you know what this one is?
Yes.
What's this one?
Songs.
No, this one is my computer froze, so I put it in the oven. So this is the idea of like, you feel like you know what you're doing, but you do not know what you're doing. Okay, so that's this bottom one. All right. I was supposed to update this slide, so just pretend like it has the homework here. It doesn't. How many people have gotten through these two? Raise your hand. Okay, was that easy? It's fun. Everyone liked it. Let's keep doing those. I hate the math ones. Okay, maybe I'll hunt a little bit better for those. What about this one?
That was actually interesting.
So you finished it? No, you didn't like it? Did you start it? Raise your hand if you started it. In the back, you didn't start it? Didn't even think about coming to class, huh?
Can I talk about it?
Yeah, go ahead.
So we kind of worked on it as a group, like me, Tom, as well, et cetera, like over Discord.
Yeah.
And we used ChatGPT to actually ask us to make the code.
Yeah.
It was really surreal seeing it being coded in front of you.
Yeah.
I was honestly expecting it not to work.
Yeah.
Kind of did.
So in fact, and I'll have it build your 2D implicit scheme at some point, probably for a homework. Maybe in this homework, I'll have you use that for Craig Nicholson. The thing is that, you know, one of the most important tools you can learn is when something is bullshit. And ChatGPT is not an artificial intelligence, regardless of what people will say. So you'll see this in social media a lot right now. People will say, oh, this AI enhanced learning. There is no such thing currently as AI. AI is a very discrete goal. What people are sort of papering over is the word machine learning, okay? And what you're looking at with ChatGPT is a text predictor, but it doesn't know what it's doing. So it knows when things look very similar. So if I have these lines, I think this is what comes next. And it's very sophisticated, but it's not actually aware, it's not cognizant of what it's written. Okay. So that being said, when we do a much harder problem, it will produce code that looks really right and yet is wrong. Okay. So be very careful when you use ChatGPT. Does that make sense? Easy stuff, it'll do well. Code that's already been written, it'll reproduce it. New stuff, like what our brains do, it has not created yet. Okay. Is everyone warmed up? Most people are present now? Okay. I know it's cold outside. Brains are cold. Let's warm them up. Start with today's activity. This one we're going to try and do in less than 30 minutes. And every day that we do it, we're going to cut it down by 5 minutes.
Let's go.
Oh, okay. Ready?
Okay.
Wait. Okay. All right. Top one. What is the name of this equation, Rolando?
Oh, I thought you were gonna go somewhere else, but continuity equation.
Okay. And what is the first term, Kobe? This one here. That's not what we're asking, remember? What does it mean in words? Paulo. The steady or unsteady term. Okay, in the back, Desiree, what's this term? This is the unsteady and steady term, and this is the... That's okay. Andrew?
The advective term.
The advective term, and what does advective mean, Andrew?
How the fluid is flowing.
Yeah, it's how it's flowing. So what's the analogy we use here for the first term, Alex?
First term, steady.
John?
How fat?
No. No, hold on. This is a conversation about fatness, but what does the first term mean? Isabel? Eating. And Giselle, what's the second term? Or reverse. And then, right? And then the food comes out. Does that make sense? And this first statement is a statement of the conservation of Jasmine in the back. What's that? This first one? Read. Mass. And so specifically this says mass cannot be created or destroyed in this system. This is not always true, but if there was anything on this right-hand side, right, then mass could be created or destroyed. So if you have some general relativistic fluid, right, which can turn energy into mass, you would put it here. No, you don't know general relativity yet. Go ahead.
Second term is the advective term, right?
Yes. Good. All right, we did it. That was like 4 minutes.
Yeah.
All right. This first, okay, sorry, this whole bottom equation, what type of equation is it, Alex? What's the name of it? It's the Navier-Stokes equation. Good. And this first term here, John?
It is the it's like as it's moving through the food itself, like all of it. Give me a second.
You're almost there.
Oh, shoot.
Anyone want to tag in?
Yeah.
Yeah.
Is it the total change in both the speed, mass of the fluid?
What do we call speed mass? Momentum, right? So this thing here is this thing here, but for momentum, right? This thing here is this thing here, because that is what we call the total derivative of the density. This is the total derivative of the momentum. So this includes two terms. What are the two terms inside here? Column? Inside of a total derivative, Kobe?
Spacing.
Another way of saying that? All right, everyone who answered that out. Okay, two terms inside of the total derivative are the steady and advective term. They're right here.
Oh,
It's the same thing.
you got this.
Okay, you see the connections yet? Okay, so we're seeing here all the ways the momentum can change are shown here. There are a lot and they're annoying. What's this first one, Jasmine? What does that mean though? You're correct that it's the pressure. And it's the pressure what?
Gradient?
There's another way of saying it with physics, yeah. Pressure forces, very good, here. And what's this one here, Desiree? The body forces, so this happens on the whole parcel. Read, what's this one?
Is that that's the stress, but yeah, diagonal.
Yeah, what does that mean? Diagonal means, sorry, say that again? Stretching and well, stretching is different from compressing.
No, like, it can do either or,
So stretching, right?
like this one.
Okay, yeah, so this would be what we call rarefaction and compression, as opposed to this, which can be considered stretching. Does that make sense? It's just weird words. Okay, so this one we call the volumetric change in the fluid, right? How does it change volumetrically? Okay, what's this one here, Rolando?
No,
What's this giant garbage one?
is that all the off diagonal terms of distress?
That's correct. That's correct. Boom! Yeah, what does that mean, Rolando?
So if you said that the one before was the diagonal,
Mhm.
if that was the diagonal stress tensor, so does that mean the term all the way to the right, that's rotation?
Doesn't have to just be rotation. Rotation is a form.
Oh, rotation is part of
Yeah, you can remember that the S or the tensor term tau has a component of S and R.
it.
So there's two parts of it. You can take your box and you can rotate it like that, right? Or you can move the box edges towards one another. If you move the box edges towards one another or far away from one another, that is the off diagonal terms. If the box moves like this, right? That's just the box moving. If the box changes like this, that's the diagonal terms. You see that?
Oh, like the S and J term, or forward is the S and J, something like that.
What's J?
Oh, I think SIJ.
Oh, SIJ. Yeah. Yeah, absolutely.
Yes, S-I-J.
Yes, absolutely. So the IJ there, when it's II, is your diagonals. When it's IJ, it's the off diagonals,
Yeah.
right? Now, IJ is sort of a bad notation because, of course, II is contained within IJ because J is going to loop through all of the parts. So we just call it the diagonal or the off diagonal. And we define these tensors like S to be symmetric, right? You define specific tensors like the rotation tensor to be anti-symmetric, right? Okay. Bottom one, questions? Okay. Next, what's the name of this top equation? Giselle.
It has to do with energy, they see that.
Very good. It does have to do with energy, and it's named after a professor in our department. Paula? John? Caloric.
Oh, caloric, yeah.
Yeah, there you go. So this is the caloric motion. That's of course not actually Andrew. This is what we're using. We're using mnemonics in our head, little ways to remember. So this is the caloric equation. And you mentioned that it had to do with energy. Good. And so what are the first two terms in there, Isabel?
One,
Very good. And the first one is? Read.
Thermal energy.
What does that mean in another word? Thermal energy, right? So it's the thermal and the bulk flows energy. Good. What's the first term here? Kobe?
Body forces.
It's not body forces anymore. John?
It's the gravitation potential.
Gravitational potential energy. Very good. So these are energy terms, right? Jose, what's the second term?
What is?
No, we just did body. We did body energy. So this is gravitational potential energy. This one is Andrew.
Sure, so. The energy imparted by pressure forces?
Yeah, so there's a different way of saying that, like pressure work, right? So if you think about your box, right? This is the work done by the pressure field, right? This is a field term. Okay, what about this one here? Alex, what's this one here?
Viscous word.
It's gonna be close to the viscous work. There is something viscousy about it.
Oh, the stress work?
That's the stress work, right? Right. Okay, and then this one here looks very similar to this one here, but a little switched up. So what's that one? Or Eduardo? Not quite. Is that? Well, we know they're all work and energy, right? So that doesn't really help us here. We want to think about what they conceptually mean. Isabel, what's this one? Okay. Desiree, do you know what this means? Okay, interesting. Okay, what about this second one? Let's move on from this one. We'll see where it goes later. What does this one do? What's that? That is the viscous force. Good. Or viscous work, sorry. And what's this last one? Paolo?
There's no the heat flow.
That is the heat flow. Okay, so now we're gonna put them in the right places. We're gonna break them all apart. Where does this first E go, Jasmine? Which direction? This way?
Oh.
This way? This way? Okay, good. All right, that's the first one. All right, where does this 1/2 U squared go, John? This way?
Yes.
Okay, this one?
Yeah.
Okay, good. All right, where does this go? Isabel? Down? Okay, good. See if that works. Where does this one?
What was the rate of UJ?
We're gonna see. So I think a lot of people have trouble with this, and once we break it down, and I'll do this again and again, you'll see the physical connection to the intellectual thought. Okay? Because they look the same, right? This looks the same as that. It's almost all the same letters, just in a jumble. And then this looks the same as that, all the same letters in a jumble. So let's think about what they influence. And what they influence is over here. So once we break these down, we're gonna reinterpret them a second time. And we're gonna be like, oh, genius, right? Okay, what does this one go to? Jose.
Down right?
This one goes here.
Yeah.
Right. This one?
Yeah.
You sure with that?
No, that one, one of them isn't one of them temperature, and the other one is like kinetic. One like the
Yeah, it's a really good question. Is that who disagrees with Jose that it goes here? Flat earthers? Okay, he's right.
Yeah.
I just wanted you guys to fight. No one fights anymore in this class. Okay, where does this one go? Desiree.
Oh, does it go like
Here,
No.
here,
Yeah,
here,
no, the part.
this one?
Yeah.
We like this one or we like it the other one?
Oh, wait, no, sorry.
This one? You like this one? Okay, who likes this one? Raise your hand. Who likes this one? Raise your hand. Okay, in fact, yes, they are parentheses because they go in the same place. Let's go. Okay, where does this one go then? This is now getting boring because the rest of them are all straightforward. Okay, so this one goes here. This one?
No.
Nope.
This one?
Yeah.
Okay, good. All right. And what about this one? Is that here? Okay, we're running out. And then the last one. Ooh, big surprise. Okay. All right. So that was easy, right?
Yeah.
We just copied them down, but some of them changed faces. Okay. So we see the UJ, the UJ, and the UI. They all decided to come hang out outside. That's a common factor. That's the U. So what does this first term mean, Kobe? This piece here? Yes, this is the kinetic energy. And what does this mean?
So I want to say kinetic energy change in space and time.
That's a different way to say it. Yeah. So it's the way that the kinetic energy is changing. Right? And we're reading this like English now. So it looks like scribbles, but we're going to understand these hieroglyphics, right? So these scribbles mean this is the way the kinetic energy can change. Okay, John, what does this mean?
And it's thermal energy, yes, thermal energy. Changing, thermal.
Almost there, just a few more words. So close. What did I say this was?
Kinetic.
Right? But what about the read?
The change, wasn't changing the change of the space and time.
Right? And a different way of saying that with just slightly different words. The ways that it can change in both space and time, right? So these are all of the ways that it can change in both space and time. So how would you then say this?
Very simple.
Do it.
Thermal energy changing. Yeah.
All the ways you can.
The ways that the thermal energy can change in space and time.
Yes.
Now, are you worried that there's no row here and there's a row here?
You divided the row.
I divided the row. Okay, so that's the reason why all these terms look different. In fact, there's a 1 over row, and over there was no run over row. That's the hint. So if I add the 1 over row, this term over here becomes that Sij that you were talking about earlier, but now it's with the product of this other one. And what is this thing looks really familiar. We're going to get to that in a few seconds. Okay, so these are all of the ways that the internal energy can change, and this is all of the ways that the kinetic energy in the fluid can change. And they're different. Okay, so what's the first one? What's the way that the kinetic energy can change, Milano?
First way that the kinetic energy can change is due to the gravitational potential energy.
Correct. Boom. And Jose, what's the second one? So it's not a force, it's a pressure work, right? So the work done by pressure in the fluid. Okay, and this last one, Paula?
The work done by stress.
The work done by stresses. And how do they actually end up working in the fluid? Like, what do they end up doing to it?
Is it like heating it up?
This is heating. This is get John's hands.
Oh, friction forces.
No, hold on. The friction forces is so this is the process of moving, right? This is the shear, but then what is the result is rotations and right strains in the fluid. This is all caused by the stresses, right, in the fluid. Okay, does that make sense?
Yes.
Yeah, okay. No, that's good. That's why we're here, right? Okay, so you start with some box. Okay, imagine the fluid flow. Oh, I'll just do it with some wonderful drawing because my drawing skill is so good. Okay, and here's the velocity flow. Okay, So that's a differential velocity flow, right? And along this box, it's going to deform the fluid, right? Oh, that's awful. So let's say it does that to the box. Okay, this is introduced what is it introduced to the box? A what? A strain, right? Is it a diagonal strain or is it an off diagonal strain? It's off diagonal because the two axes are moving towards each other. Is there rotation here? No. But the fact that I'm changing the box in this way, right? I could be, for example, imparting a fluid flow where there was none before, right? Let's say this was previously no fluid flow. Now there is fluid flow. Okay, changing the box. That's what I'm doing here. That makes sense? And it's the net flow in this box, so that's fine. Good success? Hey, Isabel, what's this first term here? This is the speed? Okay, so this is the very tricky looking VU thing. And it's neither a U nor quite a normal V. Kind of. It's not a nu either. It's just like a squiggly V. Yeah, Jasmine? Viscosity we're going to use with the... Oh, shit, where'd it go? Hold on. Oh, no. I'm going to go backwards. That's the mu. This is the viscosity term. So it looks like an M. This one that you're seeing here is this, kind of. It's actually more like this. It's not a nu. Yeah. It's volume. And so that makes this first term what, Alex?
So when you change the volume, that creates thermal.
That creates thermal energy. And another way of saying this is, Gordon? Right, yeah, but this term is sometimes also seen as a specific type of work. Yeah, Giselle? EDV work. EDV work. Yeah, you never heard of that? Okay, so PDV work, remember that we think about, this is the equation for an ideal gas. Okay, so if I can make this thing go up, then I can make this thing go up. PDV work. Right, so if I change the size of a box without doing anything to the bulk flow, right? Just expand the box or compress the box, I can make the temperatures go up and down. Okay, I'll make the pressures go up somehow, same size box, temperatures go up. Make sense?
I have a just super random question.
Yeah.
Well, this might be stupid, but I don't know, just like, you know, like there's like the CO2 cans
Mm-hmm.
and they're just very pressurized.
Yeah,
Why are they cold on the outside?
good question.
And then what would happen if you expanded the CO2 can to like the size of this room?
What?
What would happen if you just made it really big? Like the pressure inside, there's obviously still a gas in there, but it's almost a vacuum now.
I'm a little lost on your second question. So the first part is something that we can talk about, like how do refrigerators work? No, that's a question. How do refrigerators work?
Heat 'em.
They siphon heat out.
How?
Phase transition.
Phase transitions happen afterwards. What's the thing that causes the temperatures to go down? There are volumetric changes in the tubes. So for example, you can take a very thin tube and make it very big. And what would happen then? It would expand and you would lose temperature. So if you press them in and you do it the other way around, what do you do to the gas? You heat it. Okay? So these are how refrigerators work. And what you'll use is a gas like, what do they use in refrigerators? Freon, I think, which loves doing this. And then because you get this really cold gas, you then pump it through, you heat the gas up, and then you bring it out to the back of the refrigerator where there's a radiator, and you let it radiate that heat.
So is that why there's a negative term?
Yes, very good. Okay, so this is talking about a minus PdV. So if the potential energy increases, right, then PdV is changing, getting smaller. The dV there is the one that's getting smaller. You'll also notice it's not your traditional d, right? It's a total derivative. So this is both the steady and the advective way that the parcel is changing, right? Did that answer your first part of your question? What about the second part of your question that I didn't understand?
Well, if there's like a compressed gas inside of something. and
Yeah.
You made the container a lot bigger, what happens to the gas? Does it get hot? Does it get cold? Does it?
Cold. So if you take a compressed gas, right, and I increase the volume dramatically without changing the pressure, just like magic, temperature goes up. Okay. Okay.
No.
What's this? What's the second term? What kind of work? Viscous work. And so what's the analogy we like to use here? I already saw someone do it today. Read. What? What's the analogy we like to use for viscous work? I asked everyone to do it the first time we showed it in class. What? You're talking out of turn. It's unbelievable, Rolando. We've got enough points already. You're in the front row. Okay, so what was the analogy, Reed? Why? Right. Okay. So what are we thinking about? Like, what's a way to explain it to your cousin? Jasmine? Yeah. Okay, good. So that's what's happening. But can you tell them why it's happening based on what's happening here? Yeah. What's the kinetic energy though? Okay, hold on. Let's work through these thoughts a little bit more. Right on the front. Yes, there's a shear, and that's doing what? That's transporting kinetic energy, and it's turning it into heat. This is the property of viscous work. It's draining off the energy source, and it's turning it into a new type of energy, right? Because these are differentials on the velocity. Does that make sense? Okay. And this last one here, Aaron, this one. Heat flow. Very good. Is this one tricky for anyone? That one I think is like everyone agrees, except for the 1/2 rho v squared. That one most people like don't have a problem with. Is that okay? Almost perfect on time. What? No questions. We're almost perfect on time. This one?
Yeah.
Yeah, that's a good question. Desiree, what's this one? What do you mean by body work? Is there another way to say that? Very good. Yeah, perfect. Do you want to repeat that more loudly for, oh, you said in the back? Okay. Question?
What was that term that we never gave a name?
Which one?
The UJDPVX.
Wait, where? Here?
No, in the second part, the first term.
Here? Yeah, so this is like, if you're thinking about it conceptually, this is the work that pressure is doing. So if there's a pressure differential, you're going to get bulk flow. So what I mean by this is, let's imagine an atmosphere where I have a high pressure system over here and a low pressure system over here. That's going to push the flow from the high pressure system to the low pressure system without necessarily increasing the temperature. Whereas over here, this is a volumetric change in the box itself that's changing the temperature of the gas within.
The pressure was like a work done by the pressure gradient.
Exactly. So another way of thinking about this, and this is a really bad analogy, but I'm going to do it anyway. Okay. So this would be a pressure differential. Okay. Does that make sense?
Yeah.
Because there was no pressure on the other side. Zero pressure on one side, large pressure on the other. Then it moved. You see?
Yeah.
Okay. Good analogy, right? Woke everyone up. Wow, that was actually really good. We're gonna cut this down. So on Thursday or Wednesday, we're gonna be prepared to get it under 25, right? Everyone's committed to being here, ready to spit out the numbers. Okay. Let's talk really briefly about computational. We're going to talk a little bit about finite differences in a few seconds, but let's talk about some of the major thoughts that we have when we did computational. And I know you have to undelete that homework and, restore hard drive from when you took that class. But what are the 4 types of error? Raise your hand for each one. Don't just shout them. Yeah. Human error. Good. That's one of them. Kobe, what's that?
Random.
How is that different from human error? John?
Is it just like, it compiles and compiles, and then it'll like just screw up like a value and then continue to.
Yes, yeah. So everything in life is real. And even though we have our, our best efforts and attempt to build something like this, everyone agrees this is a book, right? So there's 10 to the 28 molecules probably in here. Whereas if you think about a transistor, right, those are actually looking at a charge differential with individual electrons going up and down in order to determine whether it's on or off. So those bytes can sometimes flip. That is random error. Another thing that can happen, you're doing your computation and your cat walks along and unplugs your computer, and then your power goes down for a little bit, so only part of the computation gets done, and then somehow you plug it back in and the computation starts again. That's a random error. How is that different from human error, Giselle? Yes, so human error is us writing bad code. Computers only do what we tell them to do. So if the code fucks up, it's your fault. I'm sorry. Now that's okay, because we all make a lot of mistakes when it comes to coding. What are the other 2 types of errors? Yeah. Another way of saying that? Yeah. Anything else? Yeah.
Numerical, approximation error.
Okay, you've added both of them. So which one is which?
Approximation error.
What does approximation error mean?
Since the computer can only go up to like 16 digits and stuff like that, and sometimes the values are more than 16 digits, it has to basically round off.
Okay, so you've taken both words and you put them together, but you're absolutely right conceptually. What you've described is what we call numerical round-off error, right? You can think of it as an approximation, but that kind of gets in the way of the 4th type of error, which is approximation error. Okay, so there's a little bit of a, it's easy to confuse these 2 things. One is numerical error. Numbers are not perfectly represented. So for example, E is a real number that goes on and on and on and on and on. So is pi, and yet we cut these things off because we don't have infinite memory on a computer, right? Okay. So what's that last one, approximation error? Not like
Because the equations we use are approximate.
There we go. Okay, so in fact, we recall that we're going to write the definition of a derivative. What is the definition of a derivative?
The limit as h approaches 0.
The limit as h approaches 0. F of x plus h minus f of x over h. Very good. So this is the definition of f prime of x, right? And in practice, what do we do? Yeah. No. You're right, but no, bad John. Okay, next. Just in like normal words, right? You're explaining to your cousin. Yeah.
You can't make it zeros.
Right. So this is the approximation. That limit doesn't go to 0 in our computer. If I divide by 0, I get a really bad time. So instead we make it really small. So how do I write this instead?
Drop the limit.
You drop the limit.
Yeah,
Okay, so you write something like
that, X plus, yeah, yeah, that was like, yeah. That's correct.
where delta X is finite. Right? Everyone gets this? Okay. So we have a problem, right? Computational physics is necessarily limited. Let me show you one thing really quickly. Let's imagine, and this is about as far as we're going to talk about errors in this class, because I'm going to expect you to already understand how errors propagate in this class. So we have, for example, here, delta X. Okay. And I'm going to say something like eta, which is the magnitude of the error. Okay. So if I start with really large delta X, right? Really large delta X, how does the approximation error go? Is it big or small? Big. Okay, so big is big. Good. And as I make it smaller, it does what? Goes down, right? Like that? Maybe? We don't know what the curve is, but let's just imagine. Okay, and then it goes to 0, right? Theoretically. Okay. But what's the problem?
Computers still handle really small numbers, also there's a spike at 0.
Bingo. Well, not just a spike at 0. As I get smaller, what was the other types of error that I needed to consider? One was approximation error, but one is round off or numerical error, right? And that's getting bigger. So it starts over here with a perfect representation, right? And as I step up, it gets worse and worse. So there is a sweet spot, right? Where the error is best. Make sense? Okay. So when you have your fluid dynamics and you're typing in your problem into Python and you're playing with the code and you're like, oh, I'll get it to run perfectly if I just run it at 10 billionth of a time step. What's the problem? Yes, it'll take forever, but let's say you just set it over the weekend, set it and forget it.
You're never really high.
That's what you call it. What do you guys call it?
No, it's just,
That's so when you're in grad school, you're working as long as your computer's working.
Yeah.
So this is when you become really good at climbing or snowing or snowboarding or skiing, right? Okay. So here, right? If you make it a billionth of a time step, you're getting garbage, right? Because the numerical error is going off to infinity. So there's a sweet spot. And how do I find that sweet spot?
Trial and error.
Yes and no. There's a little bit of trial and error. I do like that. So if you, in practice, let's say we give you some parameters to start with, how would you determine, see this fourth part or the third part? How do you adjust the code to determine whether or not the physics is captured? Think about it. No. You're not going to be able to intrinsically think about how a fluid should look, right? Especially computational fluid. Let's say I boil some water, right? And it shows that a plume comes up in the middle and 2 little plumes on the side. Do you intrinsically know if that's what it's going to look like?
No.
No. You'll know if it's like, hot only from the sides and then like a block of cold in the middle. You'd be like, well, that's not boiling, right? So you could use your brain that way. But once it's boiling, how do you know that you've done it right? You look at the table. No, in general, you can't. Think about your computation, right? If you build a code and you play and you create some code and no one's ever created it before, and you set it to run, it's yours. You have to verify that the authenticity of your product is correct. And so you have to test it yourself. You can compare it to other boiling, and they'll look structurally similar, but there's a way for you to be able to tell directly that your code is working.
Maybe picking an easy point to calculate and then using that recommend.
That's almost impossible.
Okay,
Yeah, no, computationally, it'll be
Yeah.
very, very difficult.
Yeah.
That's why we use a computer.
We change numbers.
Yes, what are we changing? Yes, so we have some parameters we can change, and you've already done this in your work. You can change the grid scale, right? Where the points are spaced. You can change the time step, how the time step is changed. So as you make these changes, say by a factor of 2, if you get the same result identically, you've captured the physics, right? Because an increase in resolution is not leading to a different answer. Do you see that? So then you know to stop. If you keep heading that way, then it'll change again. So what happens is you start with some garbage resolution, really large, maybe like 40 feet when you're trying to look at the dynamics of this room, just to see if it'll converge. And then you get smaller and smaller and smaller until you get the same answer a couple times, and then you stop. Make sense? Now in practice, it's not how you do it. You'll optimize, but we're not going to be perfect. Okay? Yeah.
Is that like this same idea as like the research you had us do?
Yes, but that's automated. You'll want to inspect this. So the interesting thing is this is science, right? But if you talk to any modeler, they'll say modeling is an art. It's very frustrating. There's interpretation and there's these knobs you can, oh, I like this parameter because it makes me feel good. And you're like, so okay. That makes sense? Okay. So I'm going to show you who's finished the code. Yeah, finish the code.
we kind of had something.
Were you raising your hand for yourself?
Yeah, I mean, of course I finished the code. So yeah, here's the code. Okay. So here's the solution. Let's make it a little bit bigger. Do not take a photo. This is not about getting it right, right? This is about put that down there. This is being recorded, so that's totally fine. I mean, you can grab it off there, but I want to challenge you to understand what the hell is going on. So in particular, there's a middle point. And what I'm curious about is, what are the major things that I'm doing wrong in this code so far? Why would I give myself demerits? Yeah. I didn't leave a single comment. Is that useful?
It was, yeah.
That would be.
That's yucky. Okay, so how would I leave a single comment? Okay, so. Ta-da! See, someone said it to me today. Okay, so what else am I gonna do here? What kind of comments do I want to leave in good commenting of code? Yeah.
What doesn't vary?
What they mean, right? Is this a good idea? And not really. It could be better descriptive. Sometimes you'll just have to do that, right? So like I'll write a lot of really shitty code just because it's easy to not write everything out. But then maybe I'll leave some comments for my friends, right? So I know that like someone needs to really turn this in. They're late. They want a copy. So I just give them the code. Makes sense?
Yeah.
Okay, so this section here, does this make perfect sense to folks? No, of course not. What else do I need to include here? Yeah.
Split in chunks.
Yeah, split it into chunks. That makes it a lot easier to digest both as an individual and also as someone coming along reading the code later. So I'm going to put comments in here. I'm going to break it into sections that I like. So I'm going to take all of this stuff here, probably, and put it in its own little box. So I just run it once, and then the arrays are set up, the constants are set. And then if I need to make the data a bunch of times, that'll be in here. Okay. So as I scroll down here, I have some for loops. Great, whatever. And then I have this plot.show. Why do you like that? Right. So in general, what I like to do is I like to make the data, right? So I've made a version here that I would not recommend you. This is why I told you not to take pictures of it. You'll start, the physics is in there. But what would I prefer to do instead is to save the data, right, to some form of output, some form of array. And then I could plot it however I want. So let's say I want to change the colors here from this boring blue to, a nice rainbow or whatever, like polka dots, whatever I want, I can make it possible, right? But if I have to run the data every single time, it becomes very annoying. So the data generation, the constants that we create, these are all separate ideas. And so they go into separate boxes when we use notebooks. If you're writing Python code with just a GUI and not using this, straight code, fine. But this is more fun because you can run little experiments. Everyone happy? What? No. Okay. Perfect. As long as you don't answer yourself, that's the only time that you know that you're crazy. Yeah.
I think I tried like doing like the anaconda. Like I did the code to code out. I didn't know how to work anaconda, so I'll come in like Wednesday.
Okay.
It's a statement at that point.
You can do it in CodeCalc. I don't mind that, but when you're in CodeCalc, you can download it as an IPYNB file. Just send me that file.
Okay.
I can upload it in Anaconda, and then if you want to talk on Wednesday, I can show you how to put it on your machine. Questions? Yeah.
You send email or how do you send?
You can do both. You can send it by email. I'll make sure that it works and that you didn't just copy and paste a picture on top of the output. I don't think that people would do that, but I would never even thought of that until you said it, Mateo. Great idea. Thank you. Okay. Questions, comments, concerns? Yeah. Where? I think those are, I forget what I wrote there, but I think it's just amplitude by wave. So it's a 1D problem, right? And we have some parameter f. I called it bananas when I did the original example, right? And that's being it's being advected and diffused in the fluid. And so you start with some initial parameter and you let it change through the fluid. So time is the multiple versions, right? And then that line is the distribution of that object. And so the vertical parameter is, say, bananas versus where it's located along the line, right? Okay. All right.
Wait, so I thought this was a random releasing problem.
It is. There's multiple plots.
Oh, okay. That was the unsteady advection, right?
This is a diffusive, so therefore unsteady, and advecting, right? Yeah, well, kind of. It'll like smooth out to. I mean, this is really shitty resolution, right?
Yeah.
So fluids don't look right. I purposely did it bad. Okay. Success?
Yeah.
All right. Okay, so let's talk about new material. So we're going to talk about finite volume approximation. You're already quite familiar with control volumes because you have done that on homework 4, I believe. Is that correct?
Is that?
Yeah. Yeah. So what does it mean to have a control volume? Yeah, that's the right time, 2 weeks later, right? What is a control volume? Yeah. Exactly. So I always say Amazon package, just to put into your head a box. So it is a volume. You can choose control areas, which would be, say, a surface of that box, right? And when we were deriving the equations of motion, we had this Amazon box, and we said, what can happen to it? It can get bigger and smaller. The faces of it can change. Maybe they're porous, they let fluid through, or heat out, right? Those were the ways that the control volume could undergo things, right? Okay. So in fact, we can write something like this. PVT. Okay, what does that mean? That's garbage, right? Why is there no lights? This is crazy. Give it a spotlight on it. So this first part means what? Change in time, so how something is changing in time. And this piece is the yeah, in this case it's one dimensional, but that's correct. So imagine, for example, this is a delta x. Okay, so I have x. I must, right? Okay, and then I'm gonna imagine that this is something f. Okay, and let's imagine there's a space. Okay, and this space is delta x. So what is f dx over delta x? How do I interpret that? F dx. Integral of f dx.
The area under F.
Area under f, right? So this is f, some arbitrary value. Okay, so this would be the area under that curve, right? Okay, and this is the time rate of change of that. How is it changing? Right? So this is some arbitrary curve passing through some area. So this is, for example, an average value of what's in there, right? In that volume, or sorry, in that line area. It's not three-dimensional. Okay. So how can it change? What are the ways that it can change of this arbitrary thing called f, say bananas? How can bananas change in the system?
Yeah, more or less.
You can have more or less, exactly right. So bananas can come in and bananas can go out. Right? Okay. And that's essentially what we're talking about here. So you're gonna have, say, a line in this direction, and they're separated by time. So it's two-dimensional, just like the other one is. But instead of thinking of it as taking the derivative at a location, we're thinking about what is the average value within a location delta x, right? And the mathematics works out to be fairly identical. It's almost annoyingly identical. So if you go through the process that they have in 6.2, they start with control volumes. They like go over it again, talk about how to derive an average f over a location dx. And you end up with something that looks like, let's see, where is it? Okay, hold on. All right. Oh, shit. Where is our original df/dx? So this is the finite volume equation. Okay. And it's going to be written in an unusual way. So I'm going to do j plus 1/2. Write this one. Right there. J plus 1/2 equals u over 2 f of j plus 1 plus f of j minus d f of j plus 1 j. Okay. That's not really meaningful to you yet, but if you think about the original example, finite differences, you remember what that looked like? So this is finite volume. But this one is. Okay. Don't write this all down because it's in your book.
Oh.
Is everyone writing? Oh, my bad. Okay. So conceptually, remember the whole point of this class is to understand what the hell we're doing. So one of them is finite difference and one of them is finite volume. And the geometries are different, but they're very similar. Okay. So in this first one, we derived this from saying the rate of change, say at a location here, fjn. If I want to know what it is later, then the n+1 is up here. And it's really going to be dependent on what the average value is in here at the last point, right? And so you can write it out in this way, and it looks quite similar, right? So, wait, did I miss a sign there? No, it's okay. Okay. So looking at how the fluid is moving through, say, a line, right? The formalisms are quite similar. The ways that we take the derivative are slightly different, okay? But they rely intrinsically on the values nearby, okay? The major conceptual difference between the two of them is that finite differences, not surprisingly, care about the derivatives at a point. The finite volume approximates the average to that value at a midpoint. Does that conceptually make sense? Okay. Yeah. So the finite difference, and maybe I should have kept the other one up here. So, like the way to think about this derivative here, this is evaluated at a point x, for example, right? That's how we talk about the derivative. And the way that it's written here is approximately the derivative at the point x, right? Now, the way that I construct this approximation, whether I do x plus dx minus f of x, or for example, if I do it over here, where I take a full step around that object with 2 delta x, those are all different choices we get to make. We get to call those choices different things. Like that one, you would say is forward stepping, starting at a place, I get the next place, whereas this is centered around that place, right? So this is what we call a centered space derivative, and that's a forward space derivative. I could, of course, get the opposite by going a minus delta x here, right? Just depending on which direction I'm going. Those are all approximate derivatives evaluated at a point, right? Whereas this volume version approximates the value in this region and then looks at how it's leaving or coming, right? Just the in-out that we talked about before. Does that make sense? 10%. Okay. All right. So what does it mean, explicit or implicit schemes? Scheme, that seems scary, right? Way to get your money out of your grandma, right? What's an explicit scheme to get the money? What? No, not the real definition. The definition for this class. You're right. Yeah, that you could just ask. She's a very nice grandma. She'll just give you the money. What does a scheme mean here? And then we've used it in computational before. I've kind of thrown it around. Yeah, that's exactly it. It's just like a plan to approximate a form of the derivative. Okay. So we have explicit schemes and we have implicit schemes. What do those words mean? Explicit, implicit. Kind of heard that term before. Kind of sounds like intrinsic and extrinsic. The hell did that mean? Intrinsic variables were. Yeah. Yeah. So Intrinsic relied on the stuff inside, and extrinsic was like the bulk, right? Okay. An implicit scheme and explicit scheme are going to depend on what your information depends on. Okay. So you may be asking yourself, and I know you're all just like right there with me. You're thinking to yourself, well, this doesn't make any sense, Mateo. You have this differential equation here. That's forward in time, but that's centered in space. What the hell, bro? You see it, right? This is forward in time. That's centered in space.
Oh, yes.
Of course. Does it make sense what I'm saying, or should I repeat that? Okay. So you're saying to yourself, this is forward in time. I start at a point J, or sorry, at a point N, and I go to N plus 1. Whereas for my spatial derivative, I start at N, right? Keep the same N, but look at the spatial derivative. It doesn't even include J. It's centered in space. I start where I want to take the derivative, and I will go on either side of it to get the information that I want. So that's what we call a centered space derivative and a forward time derivative. Well, they're first order differentials. So why are they not the same differential?
They like to be.
Unique New York. Okay. So this one here, let's say we make it centered space, centered time. What happens?
Going back in time.
Well, let's say I start with Nij. I'm gonna give you like N here. So this one would become N. This already is N plus 1. What's that? So this would become N plus 2. Notice the difference here? This is J minus 1 and J plus 1. That's a difference of 2, and that's why it's 2 delta X on the bottom. So this would become N plus 2, and this would become 2 delta T. That's correct. And could I ever access my N plus 1s with this scheme? No. Now they disappear. Right? And so you could do the half steps. So you could have one here that's doing all the N plus 2, N plus 4, N plus 6. And then you have a different one doing the N plus 1, N plus 3. And that's called the leapfrog method. And that actually kind of works for some gravitational codes. Okay. It'll go totally unstable here. Okay. So that's the leapfrog method, and it's unstable. Okay. You can do something called an, oh my God, we're running out of time again. Okay, it's always up. All right. You can do something called an upwind scheme. Okay. And so you can look at the flow in the direction of motion, and you can take the derivatives with respect to the direction of motion. They're also unstable. And so you're thinking to yourself, well, that's really stupid. Well, why would I take this class if everything's unstable? Okay. But there's a major problem. We've been doing this all with what I call explicit schemes, and I want to be implicit with my work. Okay, so what does that mean? What's an explicit scheme as you see it here?
It's what you're.
What's that?
So your question is, out of the finite volume and finite difference, which one's implicit and convective?
These formalisms, both here, are both explicit.
Oh, okay.
I want to build an implicit scheme, but I don't know what that means yet. What is an implicit scheme versus an explicit scheme? These are both explicit. Okay, so let's write this differently. Okay, if I'm just talking about a ball and I'm throwing a ball, okay, X at a later point, N, is dependent on what? It's kinematics. Okay, before that, position, so it's initial position, X naught, plus the velocity, times time, good. We're done? Yeah. Okay, well, we don't know what an acceleration is, right? Especially not on a computer. So you did this before, right? In computational, that was what? You did this in computation, right? This is the Euler's method. You look at the velocity at a given time. So this will be V naught. So at this time period, okay, I get the position and the velocity, and then I let time go forward. Okay, that would be this. Okay, so it gives me the next step. And if I want x2, okay, then I just say, well, I want x1 plus the new velocity v1 times a little time step, and so on and so forth. This is an explicit scheme because everything that I want depends on the stuff that I already have. Explicit, outside of the thing that I want. An implicit scheme is really fucking annoying because what it's going to do, okay, so let's say that I have an x1, it will require the derivatives at the new time. So imagine, for example, I had something that looked like this. And k is the derivatives at the new time. RK4, very good. Very good. So RK4 is a version of an implicit scheme where you're updating the parameters as you go, and you're using those new derivatives to inform you of the next step. Now, unfortunately, it gets even harder because we're thinking about a fluid. We're not thinking about a ball. So if you look at, for example, when we did this process before, and we had, say, the charge distribution, phi, that whole thing has to be solved simultaneously, right? Right? Okay. So when we think about it in the context of the work that we've already done here, oh look, I even wrote it there. You can go to higher versions of this scheme of implicit schemes. You can go to higher orders. Higher orders are just going to decrease the overall error for a given h. So that way you can beat this, right? If the higher order terms, for example, h squared goes to h to the 4, then when you have an uncertainty in the data, or sorry, in the model itself, that's going to get small with every smaller h that you choose, right? So the approximation error is going to go down more quickly. And so this will move over to the right, okay? These simultaneous solutions are going to require linear algebra. So if you took computational and you hated linear algebra, sorry, you'll need that as well. And essentially what I want to, okay, we have just barely enough time for it here. Let's look at this equation, 639. This is your version of an implicit scheme. And so what you'll see here, I should have just taken a copy and put it on there because it's so long. But essentially it's going to look like this. Okay. You're going to create something like this, Fj star. And that is Fj n plus delta E, a bunch of garbage. Okay. What does that look like? Right? Oh, it looks the same. It looks like Euler moving it forward one time step. And this will be all your old stuff. So we'll write old guard. Right? Okay. And then what you'll do is before you actually update the new parameters, so f n plus 1 at the point j, you're going to take a half step. But you're going to take it basically of the old stuff and the new stuff. So this is essentially Sense? This makes it an implicit scheme. So what I did was I calculated the derivatives based on the old values. And then I weighted it based on the old stuff and the derivatives that I'm about to get. Does that make sense? And this makes it stable. So implicit schemes, especially in fluids, are really important because they maintain stability over long time periods. Explicit schemes, except in very small circumstances like advective diffusion, they're unstable. And you can play with that. Maybe I'll create a homework problem where you just have a fluid that goes haywire. But what you do essentially is you use an easy code, something that's really simple to code up, and then you add in some terms that have nonlinearity to them, and those nonlinearities just explode. And so we saw this, for example, when you have a chord and you have the wave equation on the string, right? 2 time derivatives and 2 spatial derivatives, and you try to solve that with just the RK4, it got destroyed, right? Does anyone remember that? Too many months ago. Okay, well, it's bad, but we're gonna stop here. The next places we're going is 2D advection. That was perfect timing, I guess, because I didn't actually write anything. I was gonna do it by hand, but the 2D advection is very, very hard. Okay, what happens is every time that you've typed X, you now need to type Y. Does that make sense? That was a joke. It's not hard. Going from 1 dimension to 2 dimension just means every time you've typed X, new term, that's the Y. And so, for example, when I write the derivatives here with X plus H, you're going to have X plus H and Y plus H. We've done this before. I promise it's not too scary. If you're looking in the computational book, look for the section, I think it's 8.2, which is looking at the distribution of phi, right, in a 2D plane. So you have some array, right? And the value here depends on the values above, below, and side to side. And that's how we'll calculate our derivatives. And then you just use those same derivatives as we've done here, and we're going to apply them to advection. So now we're at 2 dimensions. You see where I'm going with this, right? Okay. After 2 dimensions, we'll talk about Bernoulli's equations, about putting them into the code. This would be steady state. We'll talk about steady state and boundary value problems. Those are easy. Those are just zeros on one side or zeros on the other. Simple. And then vorticity. Once we're at vorticity, we can almost boil water. Okay? Okay. Break. Any questions? Okay.